All right. Hello, everyone, wherever you are. Really happy to see all of you online. Welcome to the Beyond Hybrid Search with Wormhole Vectors. It's a novel idea that Trey is going to present today, and we will have a discussion. And all of you are welcome to ask questions as well. Um, yeah, cool. I think we'll start with that. This is just a quick intro from me. I'm Dmitry Khan. Most recently I'm with Ivan. I joined as a product director, leading the search domain. We offer managed open search so that you don't have your, headaches setting it up and doing some DevOps, and you can choose any cloud whatsoever, really, and then just go and run with that. And I'll share a couple of links later. I'm also a host of the Vector podcast that I started, I think, 4 years ago. I already stopped counting. Maybe some of you have heard some of the episodes, and yeah, it keeps going on and off, but I'm really excited to continue doing that. I've been in search for, I think, 16 years, maybe 20 years if I include academic, experience or exposure. I've built search at, startups, multinational technology giants. I think what was the startup, for example, AlphaSense became, I think, a unicorn company by now. Um, yeah, I'm super excited to partner with Trey AI-powered search and support from Vector Podcast. Looking forward to the session today. Over to you, Trey.
Awesome. Thanks, Dimitri. Appreciate it. And I'm really excited to have Dimitri on more for the conversation part of this. He's been doing the Vector podcast and in the space for a long time. So I think it'd be useful to help him facilitate, get lots of questions and good discussion. So I'm Trey Grainger. I'm the lead author on the book AI Powered Search, along with Doug Turnbull and Max Irwin. I'm the founder of Search Kernel, a company that does AI-powered search consulting, technical advisor to open source connections. In the last year, I've been an adjunct professor at Furman University teaching computer science. My background, basically my entire career has been in search, particularly at the intersection of data science, AI, and search. My last company prior to Search Kernel, I was the CTO of Presearch, which is a decentralized web search engine. Prior to that, I was the chief algorithms officer at LucidWorks, a search company, as well as prior to that, their SVP of engineering, and I ran search at CareerBuilder prior to that. I also a decade ago wrote Solar in Action, but AI-powered search is the focus of what I'm doing right now. The book's got quite good reviews from folks. If you haven't checked it out, please check it out. And this lightning lesson is one of a series leading up to an AI-powered search course that Doug Turnbull and I are teaching starting 2 weeks from today. If you haven't heard of it, it's kind of themed based upon the book, but we'll be going into a lot of new and emerging techniques that aren't in the book as well. Just to give you a sense, I'll spend like a minute on this, maybe two. If you're curious, it's 4 solid weeks of material. The first week we'll sort of do a course intro, introduce the search relevance problem, talk about ranking those things. We'll have a guest session from Eric Pugh from Open Source Connections talking about user behavior insights for collecting clickstream data and how to properly collect and process that. Our next session will be on signals and reflected intelligence models, everything from signals boosting for popularized relevance to learning to rank for generalized relevance to collaborative filtering and matrix factorization for personalized relevance to knowledge graph learning to learn from user behaviors, terms, misspellings, things like that about your domain. And then every week we'll have office hours where you can bring your hardest questions, or we've got labs throughout the course as well. If you need help with those, we can help. The next week we'll dive into AI-powered query modalities, things like buying coders and crossing coders, talk about chunking, talk about late interaction models, hybrid search, multimodal search, all of those. Again, all of this has code and notebooks associated with it we'll be working through. We'll have a guest lecture from Jenny from Quadrant, who will be talking about mixing sparse and dense representations with mini-coil. And then we'll dive after that into sort of hands-on building ranking classifiers or learning to rank models, uh, 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 and what is entailed in that. We will, of course, then have office hours again. The next week, we'll dive deep into RAG, talk about RAG, sort of naive RAG, agentic RAG, adaptive RAG, guardrails, all the sorts of things you need to sort of understand to RAG well. We'll talk about agentic search towards the end of the course. We'll talk about interleaving strategies for RAG. We'll have Max Irwin, our co-author on AI-powered search, giving a guest lecture. The session after that will be automating learning to rank with click models and with active learning. So we'll be diving into how to deal with biases in your data, how to deal with exploration versus exploitation, looking for results that maybe don't show up in your normal search patterns. And then the sort of final 2 weeks, we'll have a guest lecture from John Handler from OpenSearch and AWS, really talking about scaling vector search in production with lots of good experience from large scale OpenSearch clusters and Amazon servers. And then we'll dive into optimizing AI search for production, everything from quantization, re-ranking strategies, semantic caching, running local models. And then for our last session, we'll dive deep into AI-powered query understanding and agentic search, focused on really interpreting, understanding queries, leveraging agents as part of that process. And so if that's interesting to you, there's a link and a QR code here. Anyone who attends today is eligible for 20% off the course. And so definitely check it out. If you've been considering it, there's 2 weeks left. And of course, even if you can't attend all the sessions, everyone who's enrolled will have permanent access to all of the recordings, all of the code, and all the course materials. So you can use these going forward into the future if that's interesting to you. So done with that. Now I'd like to get to our topic, which is beyond hybrid search with wormhole vectors. So let me dive straight in. And feel free if you have questions, as Dmitry said, post them in the comments. Dmitry, feel free to interrupt me at any point if there's something worth diving into. Otherwise, I'm just going to keep going and kind of focus on the conversation at the end. So I'm going to start with some basic material on vectors and vector spaces to kind of set our expectations for where we're going with wormhole vectors. To start, vectors, by definition, mathematically, are something that have direction and magnitude. Vectors, if you think of them as sort of something that can go in any direction in vector space, and you can add vectors together to generate a new vector. You can average vectors together to find, sort of an area that's in between them. There's lots of mathematical operations that we can do on vectors, but let's keep in mind that they have both a direction and a magnitude. When we think of embeddings, an embedding is a set of coordinates in a vector space, in a Hilbert space, but in a semantic vector space, into which we can map a concept. So whereas vectors have dimensions, and those dimensions sort of go in any direction, when we talk about an embedding is actually a point in vector space. So for example, this point right here, this series of floats for book or tree or what have you, you can think of it as a vector originating from the origin at 0, 0 here and extending out to that point. But fundamentally, we think of an embedding as a coordinate that is a point in vector space that corresponds with some semantic meaning. In search, whenever we're dealing with embeddings, we often have things like word or phrase embeddings, where we take an individual word and leveraging a transformer model, typically, we will generate that series of floats that represents the meaning of that word, given the context around it. But we can also have sentence embeddings, where we look at all of the words in the sentence and their contextual meaning and generate an embedding that represents the meaning of the sentence. We can have paragraph embeddings that sort of summarize the core ideas of that paragraph, and the same thing with a document. Often in search, we'll start with just a document embedding, and when we take a query, we generate an embedding and we do sort of a vector similarity between them to find related documents that match the query, but you can chunk documents up in any way in any number of vectors. Conceptually, we typically think of embeddings and vectors as having a relatively small number of dimensions. We call these dense vectors, where maybe there's 768 or 1024, some number of dimensions, and we compress lots of data into a continuous space within those. However, there's also the notion of sparse vectors. And the best way to think of a sparse vector for purposes of our discussion today is to think of lexical search and to think of just, when I'm trying to run a search for keywords. So imagine you have a 1 million dimensional vector, not 768, but a million dimensions. And every single one of those dimensions corresponds to a term in your index where you've indexed all of your keywords. And let's just assume that there's only a million terms in your index. If I wanted to represent latte as a query, well, let me not do latte. Let me do donut. If I want to represent donut as a query, then I can represent that as a vector with a million zeros minus one. And there's a one in the column for donut, indicating that this is a million dimensional vector with only one value represented, and that's whether the text donut appears within this document or query. And so that's a sparse vector where it's sparse because most of the data is not filled in. I have mostly zeros, but there's some ones. And of course, in this case, if I had the search for cheese pizza, that vector would have two ones in it, one for cheese and one for pizza. So it's a million dimension vector with two ones in it. This is just as valid as a vector, as a dense vector with only 768 dimensions. But what we typically do when we start to move from lexical matching, where we can match on, those yes or no ones or zeros in an inverted index, what we typically do when we move to doing semantic search is we focus on a much smaller number of dimensions. And so conceptually, yeah, as an embedding here, what I have is 8 dimensions. Each of these items that I showed on the previous slide has dimensions indicating whether it's food, whether it's a drink, how much dairy it has, is it bread, is it caffeine, sweet, calories, healthy, etc. So you can see apple juice now is not represented as it has the word apple and it has the word juice, but it's represented as very much not food, very much a drink, no dairy, no bread, no caffeine, very high on sweet, but not all the way up, very high on calories, but all the way up, and in between, but you know, kind of sort of healthy, but not really. And then, same thing, cheese breadsticks, very much food, not a drink, good bit of dairy, very much bread, no caffeine. You get the idea. These map in the attributes or the dimensions of these concepts over here by representing them in these 8 dimensions. And in search, what we typically do is we represent documents and queries leveraging these vectors, and then we do some sort of vector similarity calculation in order to say how related or similar things are. So if I were to, for example, take the vector over here for cheese pizza, and I were to then do a cosine similarity between that vector and every other vector, I would see that cheese breadsticks have a very high similarity, followed by cinnamon breadsticks, followed by donut, all the way down to water. So these are essentially ranked based upon cheese pizza. These are the cheesiest, breadiest, unhealthiest, non-drinkiest things at the top. This is still very bready, very non-drinky, not very healthy here, ranked all the way down to it's essentially opposite in this vector space, which is water, which is all the way on the other end of the spectrum. Same thing with green tea, very similar to water, cappuccino latte, healthy, no calories drink, all the way down to a very unhealthy, very not drink. You get the idea. So that's essentially in a semantic vector space, things span across these dimensions and they fit at different places along within the vector space that corresponds to the meaning of these attributes. Now, when we deal with transformers, which we get from all the LLMs today that we're leveraging for vector search, these don't use explicit features like we have here, food, drink, dairy, bread, etc. They use latent features. And latent just means sort of hidden, or another way to put it is the dimensions don't correspond one-to-one with particular attributes. It's combinations of those dimensions together that give us our meaning. And so to think of that visually, if I were to create an embedding space, and this is obviously flattened, there could be thousands and thousands of dimensions or hundreds, but in this vector space, if these are all of the embeddings that I have, and I were to search for the keyword, or sorry, for the phrase Darth Vader, turn that into an embedding and match it, you'll see that over here on the right, I have a cluster of meaning associated with the search for Darth Vader. There's some other points in various places, but if I were to look at the items in this cluster, I see pictures of Darth Vader, which is what I would expect, because the meaning of Darth Vader is essentially in this area of vector space. Similarly, if I were to search for puppy, then this cluster of meaning right here corresponds with puppies. And indeed, I see pictures of puppies. So the interesting question arises when I ask what happens if I were to find the midpoint between puppy and Darth Vader in this semantic vector space. Uh, People have different intuitions about what actually happens here. Some people think it's, I don't know what I would find in the middle. But the answer is if this vector space is properly constructed so that the semantic meaning is represented, i.e., the further away I get from this point, the more I get away from dog, the further away I get from this, the more I get away from Darth Vader, and vice versa, then what I would expect to find if I sort of average those two, a vector from here and a vector from here together, is a puppy Darth Vader, a cute puppy Darth Vader right here in the middle. And so for some people, that makes intuitive sense. But if you think about what a semantic vector space is doing, where it's representing meaning across a continuous spectrum, you would expect to find this because I'm essentially finding what the thing is that is the average sort of in between Darth Vader and puppy within the semantic vector space. Now, there's all sorts of reasons why this could not work, depending upon how you've trained your model, and if there's too much data being compressed into to little space. But conceptually, this works. So similarly, if I were to do an embedding search for superhero flying versus superheroes flying, this is very comparable to running a search for, superhero flying sort of with the idea of a singular hero, and then subtracting out the idea of a singular and adding in the idea of a plural, again from hero to heroes. And then what happens over here is this is essentially the same vector, but moved toward or in the direction of multiple versus singular. And so what you see over here, in fact, is that while some of the images are the same, in general, I'm seeing more images of superheroes that are in groups of multiple superheroes. And so to demonstrate this with a very like explicit concrete example, if I were to take this, an embedding for this image, which is a DeLorean from Back to the Future, and I were to sort of describe it, right? This is a sporty car with, one door on either side, and it's kind of boxy and it's got really cool lighting. And so when I run that search for this embedding on other images, I find other sporty cars, obviously some DeLoreans in here, but also just in general sporty cars with, a door on either side and really cool lighting for the most part. However, what if I were to take an embedding for the query from the last slide, superhero, and I were to average that or pool it with this image embedding? What would I get? Well, in fact, we have an example of this in the AI-powered search book when we're doing multimodal search. If I take an embedding for superhero and an embedding for this image, what I in fact do get is this very first result is a sporty car with cool lighting with a superhero on top, because that's what I would expect in this semantic vector space to be in between these things. And for these other images, again, sporty cars, single door. But notice that in all of them, there's a person, and it just so happens that that person is the protagonist of their story. So maybe those stories didn't have actual superheroes, but these are the heroes of those stories. So you get the idea. And I wanted to paint that conceptually just to talk about regions of vector space and what they represent and how you can use math on vectors to move between them and sort of combine concepts and find related things. And so one problem, now zooming back out to the topic of today, one problem that we commonly come across, and this is where hybrid search comes into play, is that we have disjoint vector spaces in search, and that leads to disjoint query paradigms. And what I mean by that is that we have a sparse lexical semantic space, which is our inverted index, right? What I showed you earlier with the million dimensions and, the keywords represent the dimensions, that is a vector space. It's just a very sparse one. Similarly, we have dense vector spaces where most of our embeddings are. that we get out of large language models, where they're compact into a small number of dimensions, but they're continuous. Because we have these two different query paradigms, what often happens with vector search is we say, hey, I don't know how to combine this dense query on this embedding with this sparse query with these keywords. So I'm just going to run them as separate searches. And in fact, that's what most sort of hybrid search implementations look like out of the box. So this is an example of RRF, or the reciprocal rank fusion algorithm, where I'm essentially taking a lexical query over here for The Hobbit, and I'm matching on a bunch of documents. You'll see, each of these has the word Hobbit in it somewhere, either in the title or maybe in the description. But notice that while the first four results look pretty good, the next these were the only results that had the word Hobbit in them, and then the rest of these results, the good, the bad, and the ugly, this just happens to match on the word the three times. And then this next result happens to match on the Lord of the Rings. So it's got the in it three times as well. It happened to give me a good result, but it was purely coincidence because it doesn't have the word Hobbit here. And then I get the abyss and then the apartment again, only matching on the word the. So the lexical search found all the results that had the word Hobbit in them, but it completely missed a whole bunch of other potentially relevant results. Likewise, my vector query over here for this embedding matched The Hobbit here. It matched a Harry Potter movie here. Similar concepts, similar themes, and similar kind of visual style. Lord of the Rings, Rise of the Guardians, I guess, is maybe kind of conceptually similar, even though it's a cartoon. The Wailing, I think, just has a visually similar style, but is a really bad match. You get the idea. So there's some really good results I get from the vector search, the dense vector search, some really good results I get from this lexical or sparse vector search. And then with hybrid search, with reciprocal rank fusion, we can essentially take each of those separate sets of results and combine them together in a way that weights things that both the lexical and the dense search found relevant. It moves those to the top, and then kind of gives us better results overall. And you can see that I've matched most of the results over here. So it's better than either of the two lexical or dense vector search mechanisms individually. However, I'm still treating them as entirely separate things. I'm doing a lexical search, I'm doing an embedding search, and then I'm combining them together. But in reality, there's lots of ways to merge these different paradigms, and even beyond just the embeddings I'm getting from text. We can get text embeddings. So, for example, we can do a text encoder to generate embeddings for that. We can take images and generate embeddings for that. We can also take user behaviors and generate behavioral-based embeddings and combine those together. And there's different ways to generate new vector spaces. You can concatenate these together, and you can do dimensionality reduction, or you can stack them. I'm not going to get into those today, but the reality is we've got a lot of tools at our disposal to be able to query and get at data and relate it in different ways. In fact, what I described for hybrid search a second ago with RRF is just scratching the surface for what we can do with combining different paradigms. And so this spectrum here on the left, this is token matching, or sort of traditional lexical search. And you'll see that things like TF-IDF, Boolean matching, those kinds of things fit over here. We've also, let me just check yeah, okay. We've also got on the opposite end of the spectrum, this dense vector search. And of course, the RRF would fall in here, and this sort of hybrid sparse retrieval and dense vector search, where we're running them independently and in parallel and combining the results. But there's also mechanisms where we could, for example, run sparse retrieval first and then re-rank using dense embeddings, or something like with mini coil, which I mentioned Jenny from Quadrant is going to come talk to us about in the AI-powered search course. You can actually run a sparse search and have embeddings that are sort of adding additional semantic data to your lexical queries to be able to better leverage semantics as part of your sparse search. There's splayed, there's semantic knowledge graphs, there's all of these different techniques that we can use to get better search, whether it's hybrid search or leveraging one of the techniques. But I want to just mentioned that there's lots of ways to deal with embeddings and to deal with sparse and dense vectors to combine them to improve query understanding and to improve recall. And so one of the things that I'm experimenting with is sort of like an emerging way to do this is something I'm calling wormhole vectors. And the idea of wormhole vectors is that I've got these sort of different vector spaces. I've got my sparse lexical vector space, which we talked about. I've got my dense semantic vector space. And then I mentioned we can generate behavioral vector spaces, which I'll show in just a little bit. And so I want to walk through what this technique looks like. And I do want to frame this talk as this is sort of like new and emerging. I've got lots of experience doing some of this across different vector spaces, but there's a lot of things that I still need to iron out in terms of best practices for doing this. So treat this as something that's emerging and something you can play with, and I think the intuition will be really helpful. But if in preparation for the course and going forward, I'm going to be doing a lot more in terms of concrete examples for this. And so I don't want to get into quantum physics or, physics in general, but, wormholes, if you're not familiar, are essentially passages through space time. You can think of it as, the ability to, go from one point in space to another point in space, and essentially like hop there instantly. I could get into Einstein-Rosen bridges and all that kind of stuff, but don't really want to for purposes of today. And what I do want to do though is talk about, give me one second. Um, well, I'll skip over this. We'll maybe come to that in the Q&A if Dimitri's interested. And talking about this notion of entanglement and how that relates to wormholes. It might be interesting later, but I don't. This is about search, not about quantum physics and physics in general. So, this is what it means to generate a wormhole vector, like practically. So, if you want to generate a wormhole vector, uh, there's a fundamental base reality of all these vector spaces. Meaning, if I query with an embedding in a dense vector space, or I query with a lexical query over here, or I query with IDs and user behavior over here, all of those queries ultimately boil down to matching something. And the something that they match is really critical to how we understand queries and how we understand relevance. And what they boil down to is a document set. So if you run an embedding search over here, you find a point in vector space. And if it's a dense space, you typically do an approximate nearest neighbor algorithm or otherwise find the nearest neighbors to whatever point you're querying, and those are your relevant documents. Those documents form a set, and you can cut off the threshold at any point to say these are the documents that matched. But that set of documents collectively has some meaning that some relationships within it that represent the meaning of that query. Likewise, if I do a keyword search, I find a document set, and the collection of those documents represents the meaning of that query, at least as we've been able to represent it in that vector space. Same thing over here. So the idea of a wormhole vector is if I want to query in one vector space and find a corresponding region in another vector space that shares this sort of same meaning semantically, then what I'll do is I'll query in the current vector space, for example, with an embedding here. Actually, let me start over here. I'll query in the sparse lexical vector space. I will then find a relevant document set. This is what search does. It finds a document set. And then I will derive a wormhole vector to a corresponding region of another vector space. So for example, once I've found a document set over here, I will use that document set to generate what I'm calling a wormhole vector, but to generate a vector that will allow me to query in the other vector space or hop or traverse to the other vector space instantly to a region that shares a similar semantic meaning to the region in the lexical space. Then once I've found that vector for the other vector space, I will run that query in the other vector space to traverse to that vector space, and then I'll repeat as needed. So I can actually hop back and forth between vector spaces to find and collect documents, to try to better understand them, and then to use that understanding to take those documents and return them for the full set of search results. So I'm going to actually just show this visually for a second. Let me open up. Go. So let me click here. and restart this demo. So imagine I have a sparse vector space over here on the left. The way this works is I send a query in. This query finds a set of relevant documents that are in this vector space. And once it's found those documents, it uses them to as a essentially a wormhole. I'm going to pause this for a second. Oh, maybe I can't. Essentially, once I've run that query, I find the relevant documents, which are the things close by in vector space. I then use that to generate a vector, an embedding that I'm going to run a search for over here in the dense space. And once I run that search, you'll notice that in this example, it's not exactly where these documents are, but it's very nearby, meaning the sort of collection of these things together and what's understood semantically about the relationship maps to this point in vector space on the right. And then that allows me to then find other things surrounding it that represent a similar meaning. And this is just looking at two vector spaces, a sparse vector space and a dense vector space for keywords and then for embeddings. But as I mentioned, there's also this notion of a behavioral vector space. So the same thing happens here. I can run a query, find relevant documents, use those as my wormhole, and then I generate this wormhole vector to hop through the wormhole to the other side to find the region corresponding to that meaning in either of these other vector spaces. So in this case, if I've done matrix factorization, which is like the process you go through when you're doing collaborative filtering for recommendations, then I would hop to the corresponding region over here. So that's the general idea, just kind of visually describing it. And hop back over here. Give me just 1 second. Give me 1 second. Get my slides up. All right. And then the next question is, how do we actually create these wormhole vectors? Dmitry, if there's any questions, feel free to interrupt me at any point, but I'll keep going otherwise.
Yeah, I think we have a couple questions, but we'll defer to
Okay,
the end. Yeah,
sounds good.
thanks.
All right. So the question now is, how do we create a wormhole vector? And there's essentially two types that I'm going to focus on right now. One is the sorry, I lost the slide. Okay. The first is if I'm trying to go to a uh, dense vector space with embeddings. So this is very easy. All I have to do is pool the vectors or average the vectors of the top n documents. So imagine I run a keyword search. I find a set of documents, I rank those, and then I don't necessarily need to take the entire document set. I could, but if I want to just take the top n documents to get a more sort of semantically relevant, or just let's just say relevant set corresponding to that keyword query, then I generate a new embedding in the dense space that is just an average of those. If you go back to the Darth Vader example from earlier, where the puppy Darth Vader's in the middle, it was sort of a combination of the meaning of Darth Vader and a meaning of puppy. Think of this as taking a bunch of documents that each have their own meaning. And when I pull them together, I'm creating an embedding that has the average of the meaning. And if I assume my documents that I queried on the lexical side have some sense of a shared meaning within them, and I take the top documents from that, then that shared meaning I can hop over to the dense space, find, and then find other things that have similar meaning, even if they don't match the keywords. Likewise, I can go the other direction. If I'm in my embedding space, my dense space, I can run a search, find the top n most related embeddings by cosine, similarity, what have you. And then conceptually, it seems more difficult to then hop over to the sparse space. How do you generate a sparse vector? But there's a technique called semantic knowledge graphs, which I'll kind of walk you through, which allows you to do this. So zooming back out, I mentioned pulling the vectors of the K and N documents. All you need to do, again, I query in a lexical space, get the top K documents, get the embeddings of those documents and average them together. This is the simple way to do that, just using NumPy. For the semantic knowledge graph approach, same thing. I get the top K documents in the current vector space, and then I do a semantic knowledge graph traversal to derive a sparse lexical query that best represents those documents. And so functionally, if you think of language, I'll just talk about semantic knowledge graphs for a second and show you. The structure of natural language, you could think of it as a graph of relationships, right? We've got prefixes and suffixes, and those map to terms, those map to term sequences and documents. But once you get documents and we've got these terms across documents, you can just think of this as a giant graph of relationships. And so I can take, individual words, in this case, Trey, his, he, they all refer to the same entity. I can take other things. And if I think of this as a graph, then in fact, you can leverage your inverted index as a graph and you can traverse it to find these relationships. And so, in a typical search engine, so like any of the Lucene engines, for example, you have an inverted index, which is something that maps terms to sets of documents. And then you've got usually a forward index in, OpenSearch, Elasticsearch, Solr, any Lucene engine. This is going to be your doc values. But essentially, I can take any term and map it to a set of documents. So if I can take any term, any document and map it to a set of terms. So if I can take any term and map it to a document set, and I can take any document and map it to a set of terms, then that's a graph, and I can traverse back and forth across this. So, for example, if I have the skill of Java in the skill field, and I've got a set of documents that has the keyword Java, you can think of this set of documents as representing the keyword Java. And then similarly, they're sort of linked to other documents. You'll notice that there's no documents that link both the skill of Java and the skill of Hibernate. And so in a set theory view, it looks like this. Notice that this set doesn't intersect with these. And from a graph theory view, the same other underlying indexes look like this, where I have a graph where I've got the skill of Java with a has-related skill edge to the skill of Scala and to the skill of Hibernate, and then oncology is completely disconnected from this graph. And all I'm doing is leveraging my inverted index, my sparse representation, to traverse across these relationships. This is very useful for things like disambiguation, where I can take a keyword like server. I can traverse through documents to find, what are the top semantically related categories, for example, DevOps and travel. And then within each of those categories, I can traverse to other keywords and find which are the most semantically related keywords to server in the DevOps category. For example, I get terms like Docker, Nginx, Jenkins, Git, whereas in travel, I get things like tip, restaurant, bill, wages, things like that. And so all of this just leverages an inverted index. There's no embeddings whatsoever. This is all just leveraging the sparse uh, semantic space. But why this matters for modeling intent is if I have a query like barbecue near haystack over here, I can generate a sparse vector representing the meaning of barbecue by looking at the index and seeing what's related to it. So in this context, what I'm able to find is that barbecue is related to things like ribs and brisket and pork and the category of restaurant, i.e., I can generate a sparse lexical vector like this purely from the things that are semantically nearby in my sparse vector space to barbecue. But also, if you look at the query over on the right, barbecue grill, what I'm able to do is generate a sparse vector that is barbecue or grill or propane or charcoal. Notice that this vector is now different because it's contextualized based upon grill being in this query. So now my query becomes a category of outdoor appliance, and then this is the list of words that better represents the meaning of barbecue. Again, no embeddings, no transformer models, no LLMs involved here. This is purely leveraging my sparse lexical space and the semantics within it. And so this is some example source code from the AI Power Search book for traversing semantic knowledge graphs. But the idea here with the wormhole vectors is that I can take a query in any vector space. So for example, if I take a lexical query here, um, uh, I can easily take, lasagna or drive through or what have you, and I can generate these representations over here by taking lasagna, finding a doc set that matches that keyword, and then from that doc set, finding these other relationships. For example, lasagna can be described as Italian with keywords like lasagna, Alfredo, pasta, and Italian. And then Korean barbecue can be represented as category of Korean with terms like Korean, banchan, sariwan, etc. Fast food gets things like McDonald's and window. So this is purely leveraging, and I've been doing this for years, and it works very, very well. But this is purely leveraging the inverted index in this document set. But the idea with the wormhole vectors is not just to stay within a single uh, vector space, but to be able to go across vector spaces. So similarly, I should be able to take an embedding that finds a region in semantic vector space and a dense space, find the nearby things, which ultimately just translate to a doc set. And then from that doc set, I can use the same technique to say, what are the things that are related within these documents and generate, the similar kinds of outputs over here. You can also think of this if taking away all the wormhole vector terminology, you can think of this as just a way to make your embeddings more explainable, right? I've got an embedding, I go to a dense vector space, I find documents, and then from that set of documents, I'm now deriving a lexical vector, which is readable, that's describing what's happening there. And of course, I can then turn around and take that and query in my sparse space to match other things that have the terms but maybe didn't match in the dense space. So that's the general idea. Um, there's one kind of last thing I wanted to cover briefly, which is this notion of behavioral embedding spaces, because I've mentioned it multiple times, and I have a feeling a lot of people aren't super familiar. And so let me click here. The general idea, and I'll be very quick through this. We'll spend more time in the AI-powered search course diving into all of this, but the very high-level intuition is that when users interact with your documents, right, they run queries, they click on things, they like them, add to cart, purchase. Those are user behavioral signals. And if you've got a sufficient amount of traffic, you want to be collecting those and leveraging them to build reflected intelligence algorithms. So one of the types I mentioned several earlier, signals boosting, collaborative filtering, and matrix factorization, learning to rank, and knowledge graph learning, but specifically on collaborative filtering, which is mostly focused on personalized search, sort of understanding user behavior to generate better personalized results. We typically leverage collaborative filtering, which is an algorithm for doing recommendations. So I start with, a particular item or particular user, and I recommend other items based upon that item or user. So this is what that typically looks like, right? Somebody runs searches or purchases things like Apple and MacBook, and then these are the items they interact with, iPads and MacBook Airs, things like that. And then for that user, we can generate this list of recommendations based upon running this collaborative filtering algorithm. In this case, uh, I want to just briefly mention again that with typical content-based embeddings, I mentioned latent features earlier. Typically, you have items and there's these densely packed dimensions that represent different features collectively. Like this particular feature might have a strong correlation with size. This one might have a strong correlation with color. This one might have a strong correlation with, is this kind of like a computer? But those meanings spread across many different of these dimensions. Similarly, whenever we're doing collaborative filtering, these also rely on latent features or latent dimensions. So, for example, if I have a bunch of users, my first user likes these three movies, my next user likes these three movies, my third user likes these three, my next user likes these three, and my last user likes these three. You can kind of visually see here, these are sort of, there's some similarity here, there's some similarity here. Your brain's probably picking out what it is. But if I were to map these conceptually, I would say that users one, two, and three tended to like movies that were about superheroes made by Marvel Studios and occasionally Warner Brothers. They're all action movies and they're not suitable for small children. Whereas users four and five all liked animated movies. All of them were suitable for small children and all of them were made by Disney and Pixar. Um, a collaborative filtering algorithm sort of discovers these relationships and recommends based upon them because they exist in the underlying documents, even though we don't have them modeled out explicitly. And the way this works with collaborative filtering is we do matrix factorization. So we start with a user item matrix where here's my list of users and here's my items, and then these are sort of the amount to which they like those items. You can derive this based upon just their query and click patterns. Uh, the intermediate step for collaborative filtering is matrix factorization, which is taking this underlying user item interaction matrix and trying to break it into two different matrices. this user feature matrix, and this item feature matrix. And the idea is that if I can generate a set of latent values associated with this user across some number of dimensions, I'm only showing three here visually because it's a PowerPoint slide, but there would be more. And if I have the same latent dimensions over here for the items, when I multiply a particular user and their sort of uh, their particular values associated with these latent dimensions with the movie, then I'm pulling apart how much of this belongs to the movie and how much of this belongs to the user in terms of an interest. But at the end of the day, these are embeddings. This is a user embedding and this is an item embedding. What that means is that, and this is just how it works to do collaborative filtering and actually generate recommendations for particular items, not particularly useful for today. But what I can do is I can generate these latent embeddings, and these essentially allow me to create a behavioral embedding space for my items. So once I've done that, I can add these behavioral embeddings onto documents, just like I do with content-based embeddings, or whether it's images or text or what have you, and then leverage those as a behavioral space. So we do this commonly with personalized search, for example. We'll go through this in the course. But if I have a person who previously searched for Hello Kitty plush toy, GE electric razor, GE bright white light bulbs, Samsung stainless steel refrigerator, I can, take a normal query, keyword query for microwave, which just returns random microwaves. If I use these vectors improperly, with no guardrails, I might do things like blur the lines between categories. Most people, if they've searched for a Samsung stainless steel refrigerator, the best results here would be a Samsung stainless steel microwave. But if you do this wrong, the sort of naive approach is, I might end up with a Hello Kitty microwave or Panasonic microwave. Well, not Panasonic, but anyway, I might end up with things that don't exactly match all of the preferences within this category. Again, for another day. But this is how a behavioral vector space would typically be used. But ultimately, there's a lot of tips and tricks you can use to do AI-powered search to combine all of these different techniques that you might use to run searches and to do query understanding and relevance and sort of integrate wormhole vectors in various places. So there's lots of different query paradigms to experiment with to merge using wormhole vectors. But that's the general idea I wanted to kind of introduce today to get the discussion going about going from thinking of these vector spaces as entirely sort of orthogonal, where I have to query them separately, or maybe I could even like query them in the same query, but I'm filtering on them separately, to trying to actually pull out the semantic understanding from one vector space and use that to craft a sort of wormhole or hopping off point to another vector space to sort of continue to explore leveraging a different query paradigm. So that's pretty much it for the talk for today. Dmitry, I don't know if
Yeah,
you want to sort of dive into
great.
some questions. I
Yeah,
know some people will have to hop off at the top of the hour because this was scheduled for an hour, but I'm also happy to just kind of keep going with questions a little bit after,
yeah.
if it makes sense and people can drop off when they want. But let's maybe
Uh,
dive into some discussion.
Yeah, we have a bunch of questions. Thanks, Trey, a bunch. This is fantastic topic. I just recently traveled to Texas from Finland, and it took me like 12 hours. I wish there was a wormhole, jump through point, so I could just end up there much quicker.
That would be
Um,
awesome.
we have so many questions, man. So I'll defer my questions off, and I'll just jump. There is one logistic question from Arjun. I hope I pronounce your name correctly. I'm sorry. How is the course different from the AI-powered search book? And then later, is this topic, wormhole vectors, covered in the book?
Awesome. Okay, so I would say there's material wise, there's probably like a about a 40% overlap. Like the book is a good solid foundation for how to think about AI powered search. Obviously, we go through all the mental models and lots of code examples. So a lot of the labs and a lot of the code for the course will come from the book. However, there's a lot of new topics and things that we just like, we couldn't write 1,000-page book. And so there's a lot of things we just couldn't get to because we had to start from the beginning and frame it. And so things like late interaction models, things like agentic search that aren't in the book that like late interaction models are referenced, but we just couldn't get into depth, that are more modern and interesting ways to solve problems. Things like mini coil, which I mentioned, those things will be in the course and unique to the course, and we'll have guest speakers who are experts in those things. So I would say the course doesn't expect you to have read the book or to understand the fundamentals in the book. We'll cover those, but we won't cover everything in the book, and we'll also cover a lot of things that aren't in the book and go in deeper depth.
Yeah.
And
So
so I would say, if you've read the book, the course is still going to be like really valuable. And even if you can't make all the sessions, again, the videos and all the materials, available for you forever. But so yeah, you don't have to have read the book to take the course. But if you have read the book, the course is still going to be massively useful.
yeah, so the two
And
complement each other. And by the way, I
yeah,
own the book and it's amazing read, in silent C, and then the course is a different way of, engaging with the material, like a dynamic way. Um,
oh, I
yeah,
didn't answer the last part, which is, will wormhole
please.
vectors be covered?
Yep.
They will definitely be covered. Um, More so as like the techniques and strategies for how to hop back and forth between. So some of it's actually in the book. The semantic knowledge graph stuff's already in the book, but yeah, we'll definitely talk about wormhole vectors explicitly and have some more specific examples people can play with.
Yeah, awesome.
And I
Um,
do want to mention this is like experimental and emerging, and there's some things that I glossed over today in terms of hopping to a particular point versus trying to hop to like a region and have more of a shape that we could chat about as well. But yeah, there's uh, there's still some things I'm doing to kind of better understand and fine tune it.
yeah, awesome. I'm trying to speed up, but there is a question from Claudio. What are the latent features? It's basically where you switched from sort of explicit feature matrix to like latent features. Maybe I can take it quickly. It's basically
Sure.
in an LLM. So if you deal with an encoder model where you generate embeddings, basically these are like internal representations that the model learns, and they're like compressed. They're like abstract way of, dealing with patterns or relationships in your data. It's not exactly that, directly that black and white, but the thing is that I like on a conceptual level, these are like internal weights that the model learns. Um, then there is a question from Julianne, very concrete one. Can you give an ex concrete example of how to compute the wormhole vector from sparse to dense space?
Yeah, so I had a slide. It's sparse to dense is the easy one, which is let me go back to the slide. 1 second. Almost there. Here we go. So to go from sparse to dense, think of it this way. You've got a bunch of documents in your index, and you generate embeddings for those documents. That's how your dense space is constructed, right? Those embeddings on the documents, if you query for the documents using keywords in your sparse space, then you're still matching that set of documents, and all of those documents have the embeddings on them. So all you do is run a keyword search on your documents, take the top N documents that are the most relevant, right? They hopefully semantically represent the concept the best. And then you take those embeddings off of them and you literally average them together. The code for that is on the screen right here. And that you just generate this pooled embedding. It's that notion of Darth Vader versus puppy and finding the puppy Darth Vader in the middle, right? If someone were to, run a keyword search, and it's sort of it's easy to think of this with a single keyword, but let's go back to my what it let's go back to cheese pizza, right? Like if I search for pizza, I'm going to match a bunch of pizzas. If I search for maybe cheese pizza is bad because all pizza has cheese. Let's do cinnamon breadsticks, right? If I search for bread, I'm going to find bread. Documents that have the word bread. If I search for cinnamon, I find documents with cinnamon. If I search for sticks, I find documents with sticks. Sticks by itself isn't really what I'm looking for, but if I do cinnamon bread sticks, then I'm finding all of the documents that have those terms together, which likely are cinnamon breadsticks or have the notion of cinnamon breadsticks or talking about cinnamon breadsticks. So if I take all of those documents, the most relevant ones, and I generate and I average their embeddings together and go over to the dense space, where I land should be where the concept of cinnamon breadsticks is. and things nearby, which may not have the words cinnamon bread or sticks in them, should come back. I might get, certain kinds of donuts and certain kind. I might get like a churro or something like that. So that's how it works. But this is the math here. That's actually the easiest way is to go from sparse to dense. The dense to sparse requires a semantic knowledge graph or similar.
Awesome. I hope this answers your question, Julian. If not, feel free to unmute and ask follow-up questions. Otherwise, I'll jump to the next one from Ursula. Do we build the inverted index and the forward index to build the knowledge graph using just some documents chunks, or do we need a much bigger document base to make it work?
It's a good question. So, the best way for a semantic knowledge graph to work the best, you need to have overlaps of terms that across documents. Meaning, if I take something like Stack Exchange, um, where there's a bunch of topics being talked about, you'll have lots of people who use the same words together in the same documents. When that happens, you can easily find sets of terms that overlap commonly and use the semantic knowledge graph to generate semantic understanding and relationships based upon those co-occurrences. All the math for that's in the AI-powered search book, but that's when it works the best. Something like Wikipedia is actually, even though it's commonly used for like every data science, project, it's actually really bad for semantic knowledge graphs because every Wikipedia document tends to be about a particular topic. And other than common terminology, you tend to not have a lot of overlap across documents because they're all focused on one idea. So, for a semantic knowledge graph to work well, you typically are going to want to have overlap across your documents. What that means is that if you chunk your document so small that you only have like a couple of words or sentences or something like that, you lose a lot of that context. I mean, in general, when you chunk, you lose context. That's the problem with chunking, with most forms of chunking. And so you have to be careful not to chunk too much. But the inverse is also true. If you only have, 100 documents and every single one of them is 1,000 pages long, well, there's way too much overlap and everything is related at that point. So I would say it's no different than just how you would typically segment your documents for any search problem, right? You need to be granular enough to be useful, but not broad enough to, kind of be too general.
Yeah, awesome. Another logistical question from Arjun, whether we will share slides.
Yes,
I
absolutely.
hope
Yeah, the
yes.
video for this, everybody who signed up will get in probably like 48 hours, you'll get emailed a copy of the video so you can refer back to it. And I'll also send an email with the slides probably shortly thereafter.
Yeah, and I plan to publish this in the Vector podcast as well. So for
Yes,
those of you who want to
absolutely.
follow up later. Um, the next question is really cool from Claudio. Creating a wormhole vector that will move us from embedding space to sparse vector. I understand the methodology, but the way back, no. How do we aggregate a set of sparse vectors that represent documents in a way that will allow us to move us to the embedding space? In other words, from the sparse, like you showed, Trey, we have like
Mhm.
millions of dimensions, right? How do we compact that, right, and not lose anything and not introduce any noise when on our way to the dense space?
Yeah, so it's a really great question. I answered it technically in terms of pooling, but let me add some color to it in terms of techniques. So there's a couple of things here. One, whenever you're querying in an inverted index, there's typically a kind of Boolean matching phase, and then there's a ranking phase. Meaning, if you had 10 million documents in your index, you're not going to return a ranked list of 10 million documents. You're going to probably return the documents that have the specific keywords you searched for, which is going to be a much smaller document set. And so and you can do the same thing on the dense side with, cutoffs on cosine similarity or something like that. But step one is you start with a condensed document set that should represent generally the meaning of what you searched for using the keywords you searched for on the lexical side. However, because the idea of a wormhole vector is to find the best corresponding region in the other semantic space, It can often be useful to not take that entire document set, even matching the query. But if you feel confident about your ranking, then you can take the top N documents. So maybe you match, 10,000, and maybe you only take the top 100 and say, hey, from the top 100, if you know your relevance ranking is good, then you're going to like use that to generate a more precise wormhole vector to the meaning of those top documents over to the dense space. So, and that whether you go with the full matching document set or you go with like the top N, that's really a just practical matter of how confident you are in the ranking. If you're really confident in your relevance, you should go with the more relevant documents. And if you're not, just take the whole document set and it should sort of average out the meaning. One other thing that we didn't really get into is that the strategy, the technique I was showing. If I Let me jump back to the final slide. One second. Oh, if I jump back to here. The technique that I'm showing, where I get my document set, pull my embeddings together, that ultimately gives me a single embedding, which is a single point over here in my dense vector space. The reality is that different queries have different specificity. So imagine this is like a job search engine. If I run a search for, senior AI search engineer, late interaction, Colbert, uh, uh, signals boosting, and collaborative filter. If I run that search, that's a very specific search. Frankly, it probably doesn't match anybody, but if I ran that search, it would be a very small number of documents. It's very specific. However, and so in that case, having a point kind of makes sense. However, if I ran a search for sales, that's like a third of all jobs. And for me to take the notion of sales, which is probably a giant region in this vector space with lots of nuance inside of it, and to then turn that into just a point in the other vector space, it's probably not going to work out super well because there's probably sales is probably distributed across that other vector space in a much larger region. And so um, there's this notion of query specificity, which is also really useful. So I would actually argue that the better way to do this technique is as part of your initial query when you're sort of finding the set of documents. If you can look, for example, at the embeddings and do just like a cosine similarity across the embeddings that you're pooling, you can you can go from like a bunch of embeddings that are just pulled together into a point to actually saying what is the like relative size of the range of the cosines within these embeddings. And if it's a very large range, I understand that this is not a very specific query, it's a broad query. Therefore, when I go query in the dense space, I need to draw a larger radius or a larger kind of shape around what I'm searching for. So ideally, you're actually searching for a shape and not just a point. But literally every vector search implementation I've seen at any company is searching on embeddings as points and just looking for the nearest things, not searching on shapes. And so we don't even really have the query patterns and paradigms in place today to do that kind of a query. But I think that would be a further improvement on the paradigm here.
Awesome. Uh, yeah, Team Allison says thank you. Thanks, Team. The next question is from Julian. Can you recommend any papers or other material to explore this topic further?
Um, So, not really. So the wormhole vector thing is something I kind of came up with. I will say, well, two things. One, semantic knowledge graphs. I actually was the lead author on the original semantic knowledge graph paper back in like, I don't know, 2016 or whenever it was published. So this notion of being able to jump between spaces back to a sparse space. You could look at that paper if you want an actual research paper. I've also given lots of talks about it. It's in the AI powered search book. It'll be in the course. However, the notion of taking, running a query and pooling vectors together, and even the notion of query specificity, that cosine similarity thing. If you look at Daniel Tunkelang, he actually did a lightning talk with us a week or two ago on query understanding. He actually talks about this notion of a bag of documents to represent a query. It's functionally the exact same thing, right? So if I run a query and think of the query's meaning as being represented by the set of documents that match that query, then to take that set of documents that holds that meaning and pull the embeddings to create an average embedding that represents that meaning in an embedding space, it's functionally the same thing that Daniel describes when he talks about bags of documents. So that I would say look at Daniel's work, look at the lightning talk he gave a week or two ago with us, and those are some good resources, and of course, the book and the course.
Yeah, awesome. Maybe at some point a paper as well, right?
Yeah,
Are
it's
you
definitely possible. I need lots of
time?
good I need evals on like how this actually does in practice.
Yeah, absolutely. Arjun asked the same question. I'll skip that. Mustafa is asking for an iPhone query cases or charges may also appear. Would be correct to take the average? Would it be correct to take the average of them?
It's a good question. So yeah, if you so lexical queries work really well when you've got particular terms you're looking for, whether it's an ID or whether it's a keyword. They don't work as well with like semantic meaning. Whereas in a dense space, obviously you query on meaning, but if you try to search for a product ID in a dense space, unless you've fine-tuned it for that, it's going to do an awful job. And so in the case of like searching for iPhone and getting iPhone cases, this somewhat gets back to what I said earlier about ideally, if you take the top N documents that are the most relevant and you limit to that, like if your ranking algorithm can already sort of understand that when someone searches for iPhone that they mean you know an actual iPhone versus a case, that's a better way to go versus just anything that matches the term. That being said, um, what you can do is you can, for example, in that case, search for iPhone, find the iPhone cases along with iPhone, get that average vector, and then there's still this region of, along certain dimensions that's associated with iPhone. If you hopped over to the behavioral embedding space, what you're going to find is that, hey, these cases are very highly correlated to these items, the iPhones that actually correspond to those cases. So that might be a case where you would want to hop to the behavioral space and leverage what's there. There's also, just to note, we've talked about taking entire queries and hopping from, between spaces. But there's also a line of thinking and practice here around using this for query understanding, not just ranking. And so you could, for example, split the query into individual keywords, iPhone, like just the word iPhone and you could also search on the dense space and you could try to take the individual pieces and find things related to them and then leverage that for query understanding to hop back and forth between spaces. So the answer is you still have the fundamental limitations of each space. But imagine if somebody searched for, I want a phone that's really good at blah, 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 that's made by Apple, um, with product ID X, right? You can imagine trying to search for that like an OR query on the lexical side, and you'll actually match that ID and probably have it come up at the very top. And then you can imagine searching for that embedding on the dense space, and you could imagine for each of those hopping back and forth and trying to see what documents are there a couple of times. So look, uh, short answer, there's a lot of different ways that you could leverage this technique to be hopping back and forth. I'm not going to claim now that I've thought through every single one of them, and there's lots of ways to do it. But I think as an introduction to the topic and as a tool that you can add to your tool belt to be able to get explainability in another vector space based upon what you found in the first vector space, I think this is a really cool technique. And yeah, I just wanted to kind of present it and get feedback and enjoy this discussion.
Yeah, thanks, Trey. We're quite over time. Thanks everyone for staying on, and hopefully, if you can still stay on, we can get to the bottom of the list. Um, yeah, and by the way, to your answer, Trey, I think somewhere there is probably a notion of search result diversity as well, right? So even if the user types iPhone, they only mean the phone, but they actually may mean something else, right? So showing diverse results and then traversing to the other side with those diverse results could also make sense. Um, yeah,
Absolutely.
then Arjun is asking, is there, if I summarize the question, is there a cheaper way than using semantic knowledge graph? maybe the fear is that the graph approach is computationally expensive. Is there some cheaper way to
It's less computationally expensive than running an embedding model typically.
yeah,
But it just depends. Yeah, I mean, there's other techniques. Like if you have a fine-tuned splayed model, for example, it can give you very comparable kind of semantic understanding on the sparse side. The problem with that is you have to fine tune it to your data. And also, one of the benefits of the semantic knowledge graph is that if you, yeah, I'm just going to quickly jump to the slide to show you this one. Let me do the one that's got keywords. Here we go. Share here. With the semantic knowledge graph approach, you have the ability to not just represent the query with a bunch of terms with values, but you can actually use any field. So it's really useful to be able to describe it with a category of Korean and a bunch of terms here. And maybe you've got other fields on your documents that are really useful for describing the document, a taxonomy of some sort. The semantic knowledge graph gives you a lot richer ability to turn the set of documents into a fully expressive query. So yeah, there's other techniques. You could look at splayed, things like that, but nothing that's nearly as expressive.
yeah. And these are the concepts you're gonna cover in the course, right, Trey?
Yep,
Just checking. Yeah,
we'll cover it all in the
yeah.
course. Yep.
For those who are interested to learn more. Uh, the
And sorry,
next question is,
not trying to make this talk just a big promo for the course, but this is a
yeah, yeah,
really
yeah.
wormhole
But
vectors by themselves are a really interesting topic. But
indeed,
yeah, obviously, I would love if you would join us in the course. It'll be fun in
yeah.
November.
Debabrata is asking, what do you think about some of the reputable search sites like Indeed and LinkedIn, where searching for a male engineer will bring you results like data engineers and, whatever, unrelated stuff, not directly related stuff. And so the question is why search documents not based on the entire user query, right? Only part of it. So
Uh,
this,
I'm sorry,
this
I'm
is
trying to understand the question in relation to the wormhole vector topic.
Yeah, I think it's less directly related. I think it's more erring on the side of
It's just about data bias.
why these reputable search sites do not sort of utilize the semantic search, one to one in a way.
Yeah, I got
Like
you. I
they,
mean,
yeah.
the reality is that most AI powered search algorithms, really all of them, are use data, and the data is biased, right? So like the reality is in the world, if you look at data engineering jobs, they are more statistically skewed towards males being in those jobs than females. That doesn't mean anything in terms of who can do the job or who can't. It's just a reality that, there tend to be more males in engineering, and therefore the data is reflecting that. It would be nice to be able to take those biases out. And in fact, there's ways you can do that, but they're extra work. And so the out of the box algorithms that are typically employed don't necessarily try to tackle those biases. So yeah, I think it's valiant to, try to, especially when you're dealing with things like people's livelihoods and careers and things like that. I think it's a great exercise and something they should focus on. But it's like unfortunately kind of a reality of the underlying data that's being bubbled up, I think.
Yeah. My take is that
The
I've
data
built
is
one.
biased.
Yeah, I agree. I've built one job search engine like a couple companies ago, and my take is that probably these companies are trying to avoid, these traps when your super precise query will either lead to nothing or lead to just a couple of jobs on the screen, because their business is to show you as many jobs as possible so that they can monetize that. So it's all about maybe like business element as well. But I'm
Hmm.
sure there are other like technical aspects of this which we should not disregard.
Sure.
Um, the next question is from Arjun. In your experience, how much do the following results differ? First, query against dense vector space directly, and the second query in sparse vector space and wormhole to dense vector space, and finally get the docs that are similar to the wormhole vector averaged vector. It's a, it's a
Yeah.
loaded question.
I,
Makes sense?
I mean, at the end of the day, if you have a query that you run against your lexical space that matches mostly documents that are related to the query, and then you hop over to the dense space, you're typically going to get a lot of overlap because the lexical space semantics are going to be very similar to the dense vector space semantics in terms of like the underlying meaning. If you were to take the lexical space, and I should mention, you can actually use a wormhole vector in the same vector space. I kind of showed that with like taking a query like lasagna and then rewriting it with a more expanded out lexical query with, category of Italian. And so you don't have to actually jump between different vector spaces. You can even jump within the same vector space. And I think that in this context, the more similar the meaning of the underlying set of documents is matching each query, the more interesting you're going to be able to find missing links in the other vector space. If you have very orthogonal queries, like you can imagine on the lexical side, searching for, orange juice and Nintendo Switch, right? Like, or you'll get nothing for that, but orange juice or Nintendo Switch. Well, you basically end up with a document set that is really two separate document sets, right? It like there's not a lot of overlap, and if you hop over to the dense space and get the average of those, there's still going to be things that are like probably close to Nintendo Switch and probably close to orange juice, but the more different those things are, you might get some weird stuff in between because you're now
Yeah.
looking across two different places. Any Nintendo Switch stuff that's orange or related to juice or something might show up, but it's going to be weird. And so this isn't like a magical silver bullet that solves every query understanding or every relevance problem. It's just another tool in our toolkit to be able to better reason about the underlying documents and queries and to, explain queries in another modality, if you will, another query modality.
Yeah, in other words, what you're searching for should still kind of make sense.
Yeah,
So
yeah,
if it does, it probably will return some useful results. Tips says thank you, Tips. Rustem says, the impact of document segmentation. So basically, what are the suggestions to improve that so that wormhole vectors would be useful,
yeah. I,
especially
I
for
think
large documents?
Yeah, I mean, I think it's common sense, like the same way that you would chunk documents for doing RAG, having to think of, if you if the documents are too big, then there's too much loss of specificity and too much context being blurred together. And if the documents are too tiny, then you're losing context and they're too specific and not enough overlap. So I think, typical like whatever your domain is, I mean, if you've got giant PDFs that are books, maybe break it into chapters or possibly even sections of chapters if they're large sections. But yeah, just like use common sense. What's a reasonable size document that represents the meaning of something that is like sort of let's call it integral or like a whole thing, a whole concept.
Yeah, yeah.
It
And
depends
maybe
on the domain, but it's I would just say, your common sense is probably going to take you far on that one.
Yeah, and like for long documents that are like, I don't know, 1,000 pages, for sure you want to do that. And maybe the last question is from Arjun. Can this idea of wormhole vectors give us more serendipitous results?
Give us more what?
Serendipitous results.
Serendipitous
So,
results.
yeah.
Absolutely. So yeah, if I think of just the behavioral space, right? If I run a query, a keyword query, and then I want to find other things that are related to this that don't match the terms and maybe don't even match the meaning, but like user behavior has said that these things should suggest. I'm basically infusing recommendations then. If I hop over to the dense space, then I take my keywords and I'm finding other things that share meaning but don't necessarily have that keyword. If I'm starting with dense and I hop over to the lexical side, I'm making sure that I'm finding things with that meaning, but I'm adding in keywords that were completely ignored by the dense space. That one's not necessarily as serendipitous. That's just like fixing problems. But I would say going from lexical to semantic more so will get you things that were just missed. But yeah, for actual serendipitous, the behavioral space is probably going to give you a lot more magic there.
All right, awesome. I think it's a wrap. Thanks so much, everyone. Trey, thank you so much for the presentation, for the idea, and for pounding at the questions with such an immense speed.
Awesome.
Thank you all
Thank
for
you,
staying
everybody.
over time. This was awesome.
Awesome. Thanks, Dmitry. Really appreciate you coming on. This was awesome. Thanks, everybody, for joining. And yeah, the video and slides and everything will be coming out to you. And I hope to see you soon. Thank you.
See you soon. Bye bye.
Bye.